So our next speaker is Chia Kai Kuo, and he'll tell us about geometric transition from maximal SYM to ABJM.
Okay, thank you so much. And today I will talk about ABJM Amplituhedra, which is a very beautiful and rich and new geometry object. And we introduced this year with SYM and routine. And more importantly, this geometry object just come from simply just from a very small multiplication of the original amplitude. And we can transition our spherical model from the maximal super-YAML to the ABJM. And for the mathematician, we also know the ABJM, which is a three-dimensional field theory, and with is a Chern-Simons theory with supersymmetry extension, and very different from the YAML theory. And in my talk, I want to show how to do this two small multiplication. We can automatically satisfy all the conditions of the ABJM theory. So yeah, so in the first day, Era already get a great review for the Amplituhedra, so I will not repeat it here again. So basically, which is the geometry object with three indices, N, K, M, describe the maximal super-YAML amplitude. N is the particle number, and K is the particle helicity or the scattering configuration, and M equal 4 is related to the momentum. Is related to the momentum twistor. It has 4 components, which is a very convenient variable, and we can easily describe the panel pole just by the concentration the twistor I-1I, J-1J with the Leibniz-Sibirka tensor. And due to momentum twistor is a dual variable, so it trivializes the momentum conservation, and also, it's very easy for us to describe the massless kinematic. In other words, the new condition p squared equal to 0 also can be trivialized. So yeah, as Judith told in the beginning, we can directly define the amplitude in the kinematic space, then by stage the full place space by y per dot bosonic di. Then the 4-component twistor is parameterized by its y coordinate, where y is just the Grassmannian GRK k plus 4. Similar for loop, we can also impose the ABI plus 1 and mutual pole, which are physical pole to be positive. Also, the scientific condition k plus 2 scientific. And the super-YAML amplitude will be defined as a canonical form in this geometry. So we can introduce the Grassmann number eta by group all the field Coulomb, Guino, and all things together, such as to form a super multiply or the super field. Then our scattering amplitude become the Grassmann polynomial, which degree is 4 times k plus 2. For k equal 0, we call the NHV. For k equal 1, NHV, and so on. Here the k is the index of amplitude. So if we want to extract the particular scattering configuration, we just take the coefficient of the particular monomial. Like this example is E1, 4, E2 to 4. It describes the scattering of Coulomb with 2 negative helicity, and remaining are the positive. So now we change the variable to the momentum twistor and factor out this NHV amplitude, which will take the Grassmann degree A. And the eta I also be changed to the chi I, which is the Fermionic part of the super twistor. Then if we do the replacement by replace the Fernani Chi of the super twister to the default Li, then we can obtain the 4K form. And if we consider its loop expansion, and each loop will tell 4 degrees, so we can obtain a 4K plus 4L form in each loop order. And this 4K plus 4L form is the canonical form of the amplituhedron. So this is a combination of all the physical quantity related to the this geometry space. So now we can go to our topic of the ABJM geometry. So first we need to know what's the criteria we need to satisfy for this geometry. And since ABJM series in 3D, so we need to reduce the kinematic to the 3D. And second is the ABJM theory only has even point amplitude. So we need to remove the R point amplitude from the geometry. Also, once the n is determined, the k also be fixed by the k plus 2 equal to n over 2. So this is the 3 condition we need to is our geometry need to reflect. So the first 3D kinematic is relatively easy. Just use the conformal SU4 break down to the SP4 when we from 4 dimension to the 3 dimension. And it means that our bitwister I plus y is managed on this symplectic measure. So this kinematic will describe the 3D. And another two was seen naively was seen not so easy to achieve. So we need to kill R point and the outer K helicity. Just key this we call the middle helicity. But actually, to manifest these 2 conditions, we just need to change the sign of I plus 1 JJ plus 1 from positive to negative. And plus the original symplectic condition, these 2 conditions will automatically satisfy. So as I will show in the next slide. So here I use the concrete example for the 5 point. So here is identity. All the 4 brackets of a twister can be decomposed as a product of the 2 brackets. Here, the 2 brackets just defined as a twister contrary with a symplectic measure. And due to the symplectic condition, so if the 4 twisters are consecutive, I plus 1, I plus 2, I plus 3, then the second term and the third term will vanish. Only the single term survive. So if we consider product of 1, 2, 3, 4, and 2, 3, 4, 5, we can first decompose it as a 2 bracket. Then we replace 1, 3 to the 5, 1, 2, 3 over 5, 2, and 3, 5 to the 3, 4, 5, 1 to the 4, 1. Yeah. Then we combine the 2 bracket in the denominator to the 4, 5, 1, 2. And we can see in the beginning the sign is positive, but in the end there are 3 4 brackets which are negative sign. So totally is negative. So it leads to the contradiction. Okay. And now we see the even point. So for the 6th point, we can use a similar analysis. So this time we product these 3, 4 brackets together and do the same way. In the end, we will obtain the these 2 brackets over this 1, 5, 6, 1, 2, and rendering just the total square. So the beginning is negative, in the end also negative. So the R point is allowed. So in general endpoint, we can show that the sign of the left-hand side will be controlled by the particle number. And only when the n equal to even, yeah, this equation can hold. So this is how we kill the R multiplicity from the geometry. So it's so far so good. Yeah. So next, I show like so first, now n is the even point, so this k must be integer. So I show like can be middle. They satisfy the k plus 2 equal to n over 2. So we start with the 6th point and consider the sine flipping sequence. The k mean here has a k sine fifth of this sequence. So we can first decompose it as a 2 bracket, and we will find that this sine flipping sequence will share the 2 bracket 1, 3. So we can just draw it out, focus on the sine flipping sequence of the 2, 4, 2, 5, and 2, 6. And similarly, all the sine flipping sequence a minus a plus 1j can replace aj, 2 bracket aj. And if we arrange our sine flipping sequence in this z shape, then first the sign of this line will be alternating because these two will combine to the 1, 2, 3, 4 is negative. And similar for the this element of the sequence will also be alternating sign. So if we look at the blue line, Q2 is now is k equal 0 NHV. So the 0 sine flipping means the 2, 5 must be positive. But from the green line, we can see if it's 0 sine flipping implies 2, 5 should be negative. So we lead to the contradiction. And similarly, if we look at k equal 1, we can see that this time we have 1 sine flipped. So either the 2, 5 is positive and negative. This sequence will be 1 sine flipped. And similar for the one I circle in blue line. So yeah, k equal 1 is allowed. Yeah. So using the same way we can, I think we show up to the 14 point, the k always satisfy k plus 2 equal to n over 2. But so far we don't have the generic proof for the any point, any n. Okay. So we can now define our ABJM tree geometry by first changing this sign from positive to negative and impose the symplectic condition. And all the things just keep the sense. But now we still need to clear out the subspace, which we don't know so far. And in our paper, we give a candidate of the our amplitude need to filter out in n equal for it filter out the NHV, and we have a candidate for the filter out factor. The remaining Rn for ABJM is 3k form. So we need to clear out the 3k subspace from this kinematic. And so it's open question whether the Rn we introduce in our paper is a canonical form of this 3k subspace of the kinematic. Okay. And so motivated by the tree geometry, we can look at the loop geometry. So we also change the sign from positive to negative and impose the symplectic condition on the loop tracer. All the other things is same. And so we will define the 3L dimension geometry. And physically, the amplitude is loop integral should satisfy many consistent conditions. So the most famous one is the car condition, meaning that if we put this propagator on shell, it means the L squared equal to 0, then it will become the product of the lower point or lower loop amplitude. So like this triangle graph, if we cut the 3 cut to become the 3 4-point amplitude, its cut value will related to this product of 4-point amplitude. So from the mathematician point of view, this condition means that whether the ABJM loop amplitude is consistently factorized by itself. And in Mark's course, he talked about the boundary of the 4-point amplitude. The first is the AB line passes through the vertex, and second is passing through the 2 line. And if we further ask the line to pass through another vertex, this we call the subcut in physics. And another configuration we call the double cut. So I will check out our ABJM loop amplitude to manifest this property. So for the subcut, yes, the L loop ABJM amplitude will reduce to the L-1 loop amplitude. So geometry actually is very easy. Just the AB line reduced to the line J-1J. Then all the conditions involved AB will become trivial because AB-1I will just become the J-1J I-1I, which is negative from the kinematic. And similar for the mutual condition, it just become the CD-J-1J also is negative. So the loop of AB completely decoupled, it just become the L-1 loop geometry. And for the double cut, this cut will equal to the product of the 2 amplitude, satisfy this condition. And geometry, this factorization actually subsists from the original amplitude. The only difference is the factorization channel of ABJM is less than the super Yang-Mills. But this unwanted channel also very easily to remove because we already show that the tree region, the geometry will come, the unphysical configuration will lead to empty geometry. So this unwanted channel will just manage because the tree is 0. Okay, and the third cut condition or boundary we consider is the R-particle cut. This related to the ABJM theory only has even point amplitude. So if we isolate we import a cut to isolate the R point amplitude, this cut should be 0. So the condition for cut out to the R point amplitude is ABAJ-1J and ABBI-1I. And mutual condition equal to 0 when IJ both even and R. And to show that we can first choose these 4 twistors, J-1J and I-1I to explain our loop. And these 2 conditions will just imply the YA and WB equal to 0. And finally, the mutual condition we can will equal to this. There are 2 terms, and the first term also related to the some loop propagator with external line, so it's positive. And the second term is sign was determined by this ratio of 2 brackets. And if IJ in this case are same even or R is negative, plus this negative sign, the second term also is positive. So if we send it to 0, it requires the first term and second term will need to be 0 separately. So it's a hierarchical dimension boundary. So this cut also vanishes. Final thing is the maximal cut. And maximal cut is we at L loop we import the 3L cut condition. such that the low degree of freedom will completely determine. Maximal cut also related to the BCFW cell, and in ABJM is a cell of the positive orthogonal Grassmannian OG. So, for example, this 2-loop 8-point maximal cut is on shell diagram actually just the medial graph. It means that each vertex is quartix, and each quartix we can blow out to the on-shell diagram. And this is a book coordinate for the positive orthogonal Grassmannian. So we can also read the late right place to read which minor magnitude. So this line will imply the minor 4, 5, 6, 7 equal to 0. And another line start from A, N to 3 will imply the A, 1, 2, 3 equal to 0. So this cell is described by the 4, 5, 6, 7 and A, 1, 2, 3 equal to 0. They are component to each other. Yeah. So it's in orthogonal Grassmannian component minor always this sense. So in ABJM, the geometry also be triangulation by this BCFW cell. But in the 4-point and 6-point, it only has a single BCFW cell, which is top cell. So there's no triangulation. The first triangulation example is starting at the A point. There are two collections of BCFW cell triangulate the geometry. One is 1, 3, another is cell of 2, 4. Okay, so now we define the positive of maximal cut, and you can also mention in its talk. The positive here means that we insert the cut solution, which will completely fit the AB and loop variable, such that the inequality still holds. And if it's true, we call the maximal cut is positive. And the maximal cut is positive only if our kinematic, like this case our Li is in the corresponding Grassmann cell. So like this maximal cut we just consider is related to the cell 4. So it only positive when our kinematic is in this region. So during the amplitude, we usually reproduce the maximal cut like construct the integrand and times its cut value, such that the integrand only has positive 1 when on the cut and magnitude on other cut. But this will not the amplitude. This will not be a geometry form because we know in the 8-point this case these 4 cells actually were overlapping. So this will contribution to the BCF triangulation. So the amplitude will reproduce the maximal cut more interesting way, also related to the parameter called chamber. Yeah, it's the intersection of the BCFW cell. So the loop integrand in different chamber will have distinct loop form. So if we in the 1 intersection 2 this region, and yeah, so our loop form will display the intersection structure. So this integrand is refers to maximal cut of 1, and this integrand is related to the maximal 2, and this Bart's interval will produce a sub cut. It appears in all the region. So we use this shorthand notation to denote the I1 to this integrand and I2 to this I0 for this collection of Bart integrand. So for the region 3, 2, we just replace the 1 to 3. And our correct maximal car will reproduce from this chamber form, which produce half of the leading singularity, and the SYM intersection to reproduce another. And by summing over together, we produce the correct cut. And for the sub part, because it appears in all the regions, so you will produce the 3 amplitude. So finally, there's very special structure in the ABJM, that's a branch. So in the L loop, its maximal car will have 2 L car solution. But unlike the super Yang-Mills theory, in ABJM, the maximal only one maximal car will inside the positive region we define. And we try to find the find the region such that all the car solution were located in. So so we define the parity image of amplituhedron. So like the 6-point loop, it has 2 solutions. And one just in the positive region. Another, we define the parity map by changing the sign of tracer to 4C to the minus sign. So another solution will just be in this parity region. And we also compute its canonical form. It indeed produce the correct loop integral of this negative branch. So finally, I made some open question in the ABJM. First is, of course, as a cohedral in talk. In ABJM, we still don't have the amplituhedral map for ABJM. So the candidate is whether we can formulate this tracer Grassmann integral for ABJM to some push-forward map. But here need to be noticed is the D is not OG, is the T dual OG. And it will satisfy the orthogonal condition is depend on the kinematic. Another open question is the parity amplituhedron. So all the good property was shown in the positive branch. So whether this property can extend to other branch. Also, it's really the parity map we define can cover all the branches in the ABJM for higher n. So in the A point, we define the 2 parity operation. It indeed can produce the 4 branches at the A point. But for higher n, we still unknown. So this is a conclusion. So we just add the symplectic condition and changing the sign, we can define the ABJM amplituhedron which manifests many properties of the ABJM amplitude. But second is we don't know the true amplituhedron for ABJM. And the last one is we need to understand more about this spatial branch structure in ABJM. So this is my talk.